Hello everyone. In this video we are going to discuss our first problem of week 1. So the problem says that you have a unit square and you are placing 9 points within it. So you have to show that there will always exist 3 distinct points such that the triangle formed by those 3 points, that triangle's area will be lesser than or equals to 8. Let's see how we can solve this. So now how do we get those special 3 points? That's the question. So let's divide the square into 4 equal parts. That means you have the side lengths of the smaller squares to be half unit length. Now you are placing 9 points. So by PHP or pigeonhole principle, you can say that at least one of the square will have 3 points. One of the smaller square will contain 3 points. Why? Because suppose if you argue with me that no, none of them will contain 3 points, so then at most they can have 2 points. But if these 4 squares have at most 2 points, so that means you are placing at most 8 points, but you have to place 9 points. So at least one of the square will have 3 points. So without loss of generality, let's take that those 3 points are within this square. So I have 3 points here anywhere, and now I have to show that wherever they are within that smaller square, their area is always lesser than equals to the area of the triangle formed by them is lesser than equals to 1 over 8. So now this brings us to another problem, that if we have a square, then what is the maximum area of a triangle placed within this square? So maximum area of a triangle placed within a square of side length A, suppose. So here the side lengths are A unit. So now suppose if you have any triangle inside the square, you can always increase the height of it or increase the base of it. So what we know is that the area of the triangle is half into base times height. So now, keeping the base constant, if we increase the height of the triangle, then the area will increase, right? Or else, if we just keep the height same and increase the base, then the area of the triangle will again increase, right? And so this tells us that the vertices of the triangle will be on the boundary. So to get the maximum area of the triangle, the vertices of the triangle has to be on the boundary, because given any triangle strictly inside the square, you can always increase the base or the height and take the vertices to the boundary, so that the area is more than the triangle that you had. So conclusion 1, vertices of the triangle will be on the boundary. of the square. Okay, so now the vertices are on the boundary of the square. So now there can be two possible cases. The vertices are strictly on three different sides of the square. So now let's analyze in this case. What happens is, so what you can do is, suppose if this is the base of the triangle, and so you can simply drag the base down without changing the length of the base, so that this point at some point of time, this point will come here, and this point will somewhere come here, and you will have a new triangle whose height is more than the original triangle that you had, and its base is the same, so you have more area now. So we see that we can always, in this case, we can always drag a point to the corner of the square and maximize our area of the triangle. So now let's come to the second case, that is, two points are on one side of the square and the other point might be somewhere here or here, they are both the same, or somewhere here. So let's take the first case, that the point is here. So then you can see that very well, that if you suppose this is the base, and if you just drag this point to the corner of the square, then your area gets maximized. Or if you just drag these 2 points to the two corners, then also your area gets maximized. So by maximizing, I mean maximizing the area of the triangle, keeping the base constant or the height constant. So similarly, if your point is here on that side, then you can simply maximize the area of the triangle by pulling these 2 points to the corners of the square, right? And thus maximizing your area of the triangle. So always we see that at least one point will be on the corner of the square. So here our conclusion too. At least one vertex will be on the corner point of the square. So now we have a square, and we know that to gain the maximum area of the triangle, one of the vertex has to be on one of the corners of the square. So if suppose we have a vertex at this corner, now we want to make our triangle of maximum area, then you see that this half into base into height, so the maximum base length that can be attained will be the length of the square, and also the maximum height that can be attained by the triangle will be the length of the square. And so suppose if we take the other point here and take this as the base, then we have attained our maximum base length. And if we take the third point on this line of the square, on this boundary line, then we will have the maximum height attained by the triangle. And so your triangle will then have the maximum area. So if your side length is a unit, then your area of the triangle is nothing but half a into a, that is half a square. And now let's get back to our original problem. So here we had the side length to be half. So the maximum area attained by the triangle formed by those 3 points within a smaller square here will be half times, and side length is half, so that is half square, and which is nothing but 1/8.